Okay, this is the first hour of Physics 1C for December 13th, and we're going to first start talking about sinusoidal electromagnetic waves. Toward the end of last class, we learned that electromagnetic waves are going to have a solution for their electric and magnetic fields that satisfy this equation. If you take the derivative of the electric field in the x direction, and the one we were looking at, we were taking the y component of the electric fields, and we say that if you take the partial with respect to x of this, the second partial, that it should be equal to 1 over the velocity of light squared times the second partial of the same field, EY, the same component of the field, if we take the derivative with respect to time twice. This is the equation that we got by solving Maxwell's equations. And we want to look at solutions of this. So the question would be, what kind of things EY actually satisfy this equation? And I said last time that in general, any equation that has a function of, that looks like this basically, if you have some equation EY of x and t that looks like this, that any function like this will automatically solve the equation. But there's another type of solution that we can look at, and for this we go back to something that, it depends if you've taken 1B or not, but whether you have or not, in Physics 1B we learned that if you have a wave on a string, then you can write an equation for a wave on a string where y is the kind of transverse motion of the string up and down, and it looks something like this. I guess we're going to use sine. I don't think it matters if we use cosine or sine, but we're going to use sine, I think. I'm going to be consistent with the book, because the book uses cosine, the book does use cosine. So we'll use cosine. Okay, so y of x and t, a cosine kx minus omega t. Now, in this equation, and we're going to have a similar equation for the electric field, the k and the omega may be new to you. I don't know. You've probably seen the omega before. K is what's called wave number. It's 2 pi divided by lambda, where lambda is wavelength, and omega is 2 pi times frequency, or the same thing as 2 pi divided by period. To remind you what these things are, in case for some reason you don't know much about waves, suppose that I have a coordinate system where this is the x direction and this is the y direction, and I have a sinusoidal wave that looks like this. Then the wavelength is the length between 2 points, so between here and here, 2 points that are at the same phase of the wave, so like 2 minimum will be separated by 1 wavelength lambda, or you could do 2 maxima too. This distance between here and here would also be 1 wavelength lambda, and then period t would be the time that it takes for the wave to get from this point to this point, and then you can go back and define omega that way too. So in terms of time between these 2 points here would also be 1 wavelength, or I guess you would say the time that it takes for the wave to travel from this point to this point would be the period t, and then you can define omega using that. So we're going to go with a similar type of method. So this is what we use for waves on strings in chapter, I think it's chapter 15 in the textbook. And if you took Physics 1B, then you probably talked about this. If you haven't, then maybe you will at some point in the future. So we're going to look at a solution for EY, the electric field, that looks just like this, where now, we're going to have, in this direction, it's still the y direction, but it's going to be the y component of the electric field that's going to show up. And we're going to say that our electric field as a function of x and t, just the y component of it, is going to be equal to some E maximum right here, which is just going to be the amplitude of the electric field, the largest size that it gets, times the cosine of kx minus omega t. And this same equation, we could write the exact same equation down for the magnetic field, except when we did the solution for the magnetic field, it was the z component of the magnetic field. So this is going to be bz of x and t is going to be some b max times the cosine of kx minus omega t. And so this is what we're going to use for, this is a sinusoidal wave, and it's a traveling wave too. It's not like a standing wave, okay? So any questions in general about this so far? Okay, so another way we can write this is to, if we want to just write the EY, we can also write this using like vector notation if we want to. So we can write the vector E as a function of x and t would be equal to j hat times E max cosine of kx minus omega t. This would allow us to see that this was the y component if we put the j hat thing here. We can do the same thing for the magnetic fields as a function of x and t. This would have to have a k hat, and then b max cosine of kx minus omega t. And then if we write these things like this, then we can see things like that. If we do E cross B, one of the features that we said at the beginning of talking about electromagnetic waves is that if we do E cross B, that this should give us the direction of the velocity of the wave. So in this case, if you do E cross B, does that work out if we do J cross K? Yeah, J cross K is ICAT, right? So that works out if we write them like that. If we wanted to make it so that the wave traveled in the negative x direction, then we would just make one of these negative. Like if this was negative j hat E max, or if this was negative k hat this, then you put a negative sign on here and you would get a negative I hat, which is what you want. Okay, so let's look at a problem that we can solve. I say this second version here just to say that we derived the wave equation using just one component of the electric field, EY. But now that we have it, we could in principle have an electric field where this was the z component of the electric field by putting a k hat here, or the x component of the electric field by putting an I hat here. But I think because we're talking about a wave that's usually propagating along the x direction, this unit vector is either going to be jk or negative j or negative k. Those are going to be kind of our options if we want to have a wave that travels in the x direction. Otherwise, we're going to have the wave be a function of like y and t if we want to get a wave traveling in some other way. All right, so given that setup, let's look at solving this problem right here. Let's see if I can leave some of this stuff on the board. As long as I can leave just these two equations, that's fine. And I can zoom out just a little bit, right? Because it was kind of close. Okay, it says a carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in a vacuum in the negative x direction. And they give us a picture here of what this looks like. The wavelength is 10.6 micrometers. So wavelength lambda, oh, the thing moved as I was typing. Lambda is 10.6 micrometers. I could probably make this bigger. This is probably hard to read. Okay. It travels in the negative x direction, so we know that the velocity is equal to, we could say, negative c I hat, because c is the speed of light. It says the electric field is parallel to the z-axis, so we know that if we look at the electric field, it's going to be equal to some Ez times parallel to the z-axis, right? K hat. And it says we want to the wavelength is this. The E field is parallel to the z-axis. We also know that E max is 1.5 megavolts per meter. Where mega is 10 to the 6th. We want to write vector equations for the electric field and the magnetic field as a function of time and position. Okay, so we've got this picture here where we have our electric field. It's oscillating in the z, what do you call this? The zx plane. Yes, the zx plane. So the electric field is always perpendicular to the x-axis. It's also always perpendicular. No, that's not true. But yeah, there's our electric field. There's our magnetic field. And we want to write vector equations for each one of them. So let's start off with the electric field. It should be pretty easy from the given information. So we're going to need to know two things. If we want to write an equation that looks like this, we need to know the direction that's oscillating in. We know that part. I'm not going to start writing it down yet. We know this is going to be a k hat. And then we have Emax is given. So we just need to find k and omega. So we're given lambda. And we can find the wave number k by doing 2 pi divided by the wavelength that's given. So that's 2 pi divided by 10.6 micrometers, which would be 10.6 times 10 to the minus 6 meters. So we get, this number's huge, 592. I'm going to write this as 5.93 times 10 to the 5. The units for K are radians over meters. Obviously, you can see the meters down here, but this is like 2 pi radians per meter. So that's K. We also need to find omega. From above, we know that omega is equal to 2 pi multiplied by the frequency of the wave. And we also, I'll write this up here, we know that the velocity of the wave is equal to the wavelength multiplied by the frequency, which means that the frequency is going to be equal to velocity divided by wavelength. So that means that our omega, the angular frequency, is going to be 2 pi times the velocity of the wave divided by frequency. And I guess really what I should be using, since we're talking about, this is such a weird time in the semester for me. I'm teaching 1B and 1C. We're doing sound waves in one class, and we're doing light waves in this class. And they're very similar to each other, except I have to replace velocity with the speed of light. We always use c for that. Okay, so if we then plug in our numbers here to find omega, we're going to have 2 pi. The speed of light is about 3 times 10 to the 8 meters per second. We divide that by the frequency f, which is... Wait a minute, we're solving for frequency. I'm sorry. That should be wavelength, because we're replacing f with c over lambda. There we go. And our lambda was 10.6 times 10 to the minus 6 meters. So this should be equal to omega. And if we solve this out, we're going to get that omega is 1.78. We'll just do, I guess we got 1.78 times 10 to the 14 hertz. It's not hertz, sorry. This one's going to be in radians per second. Frequency's measured in hertz. This one's measured in radians per second. This is pretty close to visible light. What did they say this was? It says carbon dioxide wave here. It doesn't say if it's visible light or not. Oh, infrared. That's what it says. Okay. It's pretty close to visible. All right. So that's our omega. So we have omega here. We have lambda here. No, not lambda. Sorry. That one's K. Wave number. And now we should be able to write our equation for this. So the next, well, I guess we'll go ahead and write that one down. So the first answer is going to be E of x and t is going to be equal to, it's oscillating in the plus and minus z direction, as you can see here. So we're going to have k hat times E max k hat, not to be confused with wave number k, it's kind of confusing, and then cosine of kx minus omega t, and then we just plug the numbers in. Okay, E max is 1.5 megavolts per meter. Okay, I kind of don't want to write these units in here, but we'll write them anyway. 5.93 times 10 to the 5 radians over meters times x minus, and then omega 1.78 times 10 to the 14 radians over seconds times t. Just barely fit that in there. So that's the answer to the electric field part. Now, the magnetic field part's going to be very similar. It's going to have the same cosine of all of this junk, but the magnetic field is oscillating in the y direction. So in front of here, we're going to have to put j hat. It may have to be negative j hat. I have to think about this, because we want it to go in the negative c direction. We want it to go, in the negative x direction here, right? So if we do k cross j, what does k cross j equal to? Can you all tell me what's k cross j equal to? K hat cross j hat. It's got to be I hat, but is it positive I hat or is it negative I hat? You can use the right-hand rule to figure it out. It's negative I hat, I think that's right. You can either do k cross j, which is like this, and your thumb points this way, or you can use the trick that I think I showed you, where if you go backwards in the alphabet, going from a cyclical alphabet where it goes I, J, K, I, if you go backwards from k to j, then you get negative I hat, and if you go forwards from j to k, you get positive I hat. So it's negative I hat, which is good. So that means we do want this to be positive j hat, but if we needed it to go the other direction, we may have to put like a negative sign on one of these, right? So just keep that in mind. All right, so the other thing is, what is B max going to be equal to? That's the next part we didn't calculate yet. So how do we find B max? Any ideas? Yeah, we can use the fact that the maximum amplitudes are going to be related to each other by the ratio that E is equal to C times B. That's right. So we do E max is equal to C times B max. And then we can just solve for B max. So then B max will be equal to, E max is 1.5 times 10 to the 6th volts over meters. And then we divide that by the speed of light, 3 times 10 to the 8th. That should give us our magnetic field. So this one comes out to be 0.005. And the unit should be Teslas. Volts over meters divided by meters, so it's going to be volts over meters squared per second, which should be, that's definitely what a Tesla is. Okay, so we get J hat is this times 0.005 Teslas, and then all the rest of the stuff's the same, so I'll just copy it. And that is a relatively simple problem for this kind of thing. Anyone have any questions? It's pretty easy, right? It's just a you're just trying to fit things into this formula here, and you just need to know some of these relationships, like how do you find K, how do you find omega, and then this one down here, how do you find the relationship between these fields when you're only given one. That's pretty much it. I guess you need this one too. But as long as you know those relationships, you just plug things in, and yeah. You have to think about the direction of travel. You have to think about what plane it's oscillating in. You know, one thing to mention, by the way, is that while we're describing light in this way, the picture that I'm showing you is it's very simplistic. What we're talking about is a special type of light, and I'm not going to go into a lot of details, but to say that normally when you look at light, like let's say the light that's coming from the sun, or the light that's coming from the headlights of an automobile, for example, the light isn't only oscillating, like let's say just the electric field, it's not only oscillating in the z direction. What you have is multiple light waves that are oscillating all on different axes, okay? And so suppose that you think about the light wave coming towards you, and I tell you that one component of the light wave is oscillating back and forth like this, okay? So the light wave's coming out towards you here, right? Light is composed of light waves that are also oscillating up and down like this, also oscillating back and forth like this, and then basically at every angle you can possibly imagine, okay? And when you have light that's only oscillating up and down like this as it comes towards you, we say that that light is linearly polarized. You've probably heard of like polarizing sunglasses. And what polarizing sunglasses do is they effectively tend to block out some of the light by applying a filter at a right angle or at a 45-degree angle to the way that the light's moving. Anyway, you'll learn all about this if you take Physics 1D or if you've studied optics in any way. But I just want to make you understand that, or help you to understand that, even though we're talking about light waves that are only oscillating like this, real light waves oscillate basically in every single way. And it's only through the use of something called a polarizer that we can force the light to go from this type of profile to only oscillating up and down like this. That's what a polarizer does, basically. Anyway, that's all stuff to be learned about in Physics 1D when you go into way more details about the way optics works. I just didn't want you to think that light was this simple, although sometimes it is. When light bounces off of a lake or off of your dashboard, it actually goes from looking like this to looking like this. And that's why polarized sunglasses work really well. They're really good for getting rid of glare. Like off of your, like when you're driving down the road and it's like the early morning and the light shines down off of your dashboard and then it shines up into your eyes. There's like a glare that makes it difficult to see. That's what the light's good for. Same thing is true if you're like out on the ocean or out on the lake early in the morning when the sun's rising and there's like a big glare coming off the lake. Polarized sunglasses are really good at getting rid of that because after the light gets reflected, it goes from being, we call this circular polarization to linear polarization. All right, I'm using a lot of words there that you may not have heard before, but I think it's relevant because I want you to understand when you do take Physics 1D that you will eventually come back to this concept of this oscillation of light, and just something to keep in mind. Okay. Any questions? Okay. So the next thing we want to talk about is energy and momentum in light waves. Okay, so we're going to come up with a way of understanding what happens when a light wave is traveling through the air, and we want to understand how much energy does it carry. So for example, we know that the sun is sending energy to our planet in the form of light. That light energy heats our planet through radiation. Radiation is the type of heat energy that can travel through vacuum, and it also provides, obviously, the ability to see things, and that's because the light will bounce off of surfaces and then transport that energy to you, but light waves carry energy, and we'd like to know exactly how much energy they carry. So if we go back really far to when we were talking about capacitors, we learned that for an electric field, the energy density of an electric field was given by this expression, 1/2 epsilon naught times the electric field squared. I don't know if you all remember this, but it's pretty easy to derive. And to be clear what's being described here, this is the energy per unit volume carried by an electric field. So we'll just write it as the energy per volume. So it's energy density, right? And the simplest way to derive this is just take a capacitor, write down the expression for the energy stored in the capacitor, and then divide by the volume, and you can prove that you get exactly this relationship here. It's very, very easy to derive. We did it in class, and you can go back and look at the derivation if you want to go back into the capacitor chapter. And then in the chapter on inductance, when we discussed inductors and the way that they can hold magnetic energy, we saw that you can have a similar expression for an inductor and the energy that it carries, and it looks something like this. And once again, this is the energy per unit volume now of B, which is the magnetic field, right? So we know that the electric field and the magnetic field have an energy associated with them. And in general, if you have an electric and a magnetic field, right, then your total energy density you would get by taking the sum of the electric field energy plus the magnetic field energy. And if we do that, what we'll get is something like this: 1/2 epsilon naught E squared plus 1/2 mu naught B squared. And what we can do now is we can say, well, we know that there is a connection between electric field, magnetic field, and all of these constants right here. And the connection is that we know that c, the speed of light, is equal to 1 divided by the square root of epsilon naught times mu naught. And when we're talking about electromagnetic waves, where the electric field and the magnetic fields are always in sync with one another, we also know that, as we used in the previous problem, the electric field is proportional to the magnetic field by using this equation right here. So we can replace whichever one we want to. We're going to replace the magnetic field. So we're going to use B equal to E over C. And we're going to replace that here. So B now is going to become E squared over C squared. And now we're going to just simplify things. So we have, every term has a 1/2 and an E squared in it now. And what we have left over is, from the first term, we have epsilon naught, plus the second term is going to have a 1 divided by mu naught times C squared. And what we're going to do is we're going to try to eliminate both of these variables here, because we know that C is equal to this, right? So 1 over C squared, which is what shows up in this equation here, 1 over C squared, is going to be equal to the inverse of this squared, which would be epsilon naught times mu naught. So if we plug that in here, our energy per unit volume for our electromagnetic waves at a point in space is going to be 1/2 E squared epsilon naught plus 1 over C squared gets replaced by this over mu naught. And then the mu naughts cancel. We have epsilon naught plus epsilon naught, which will be 2 epsilon naught, which will cancel out with this 2. And so we get epsilon naught times E squared. That is the energy per unit volume in an electromagnetic wave. Okay, any questions about that before we go through another kind of derivation? All right. So now what we're going to do is we're going to derive the Poynting vector from this. So we want to derive this thing called the Poynting vector, right? The Poynting vector is basically a way of describing the rate of energy flow for an electromagnetic wave, okay? So we consider the following scenario. Let's start off with a coordinate system. so that we have the xy like this, and the z coming out this way. So we'll draw a z-axis on there. It's someone's name, but you know, it does the, it is a vector, and it is going to point in the direction of the electromagnetic energy, but it's, I think it's someone's name, right? Yeah, British physicist John Poynting, who lived from 1852 to 1914, they tell us. Okay, so when we were discussing electromagnetic waves, we were talking about electromagnetic plane waves. And so the way we investigated these waves, right, is that we pretty much drew like a plane within this three-dimensional coordinate system. And so let's do that again. Let's draw some plane waves inside of here. Two different plane wave fronts. So we'll have one wave front that will start like right here. I'm trying to make this straight. It's so hard to get these to be straight though. If you're off by like 1 pixel, that's kind of okay, I guess. Okay, so we make a plane wave that's going to start off here. I have to make this look like it's kind of parallel to the... We'll line it up and we're done. Let's see. If I hold... I won't let me. Well, we'll just have to go with that. We'll have to imagine that there's a line... Nope, that looks bad, actually, if I do that. Let's see. So we want these to be... maybe more like that. Because I want... if I drew a line from here to here, I want it to be parallel with that. Let's see what happens when I draw a line from there to there. See if it looks parallel. So that's kind of parallel-ish. So we do that. That looks fine. That's good enough, I think, for what we want to do. Okay, so here's our plane. And if you remember the way that we were discussing these things, within a given plane, there was an electric and a magnetic field that was oscillating. So let's draw those in here as well. So let's use blue. So we would have like electric field vectors in this plane, right? That would be pointing up like this. And then we'd have magnetic field vectors, I'll use purple, that would be kind of pointing parallel to the edges of the plane like this, right? And we said that we had, here before I actually do this, we're going to copy this, paste it down here. So the way we described this was we said that in a given plane, we have individual values of the electric field and the magnetic field. So this would be the electric field here, probably like the y component of the electric field if it was oscillating up and down in the y direction. Remember that the idea is that the wave is oscillating like this, but if we intersect that wave with a plane, then we get the magnitude of the electric field on that plane. And since we're talking about waves coming from a distant source, the idea would be that whatever the magnitude of the electric field here is the same as the magnitude of the electric field here on a given plane, and then this is the magnetic field, and this is the magnetic field. But then that when you go to the second plane, which is going to be next to it, we're just going to copy and paste it. So we have another plane here, a little bit farther over on the x-axis. Now what happens is that these vectors are going to change. We're just going to shrink them down a little bit here to indicate that the vectors themselves have changed. But on our second plane, all those vectors, again, have to kind of be the same. So this is our picture of plane electromagnetic waves, where we can split our wave up into a bunch of different plane wavefronts. And now what we're going to do is we're going to talk about the energy that's carried inside of the volume of this wave. Because after all, what we have from the derivation we just went through here is the energy per unit volume. So we're gonna calculate the energy contained between two planes, basically. So if we go and draw here, let's use one of these ones. If I go draw a line like this, we can say that since our plane wave is moving with a speed, so the wave is moving in this direction with the velocity equal to the speed of light, then if we say that these two waves are separated by some time interval that we call dt, we can say the distance between the wavefronts is going to be c times dt, right there. And we're also going to need some area, right? So let's say that the area of our wave is a, or of our wavefront that we're looking at is a. Okay, so this is A, and this has area A2. So we can then say that the volume between these fronts, we're going to call that dV, is going to be equal to the area A multiplied by c dt. And then we'll say that the energy inside of that packet, the energy in the volume, you might say, the energy that's in this region here between these two planes, we're going to call this du. We'll use a capital U, is going to be equal to the energy per unit volume, which we have from right here, U, multiplied by dV, because this is basically energy over volume. So if we take that and we multiply by volume, right, we're going to get what we want. So U is epsilon naught E squared multiplied by the area A and then C dt. And then what we're going to do is we're going to talk about the energy flow per unit time per unit area. Well, I'll write it in words. The energy flow per second, let's say, also divided by the area, and it'll become very clear why we have to divide by area in a second, should be equal to basically du over dt times 1 over a. And if we eliminate all of those things, what we're left with is what? Epsilon naught E squared times C. Let's think about what this represents before we go in and do some more mathematics with it, just so we understand what we're talking about here. If I talk about energy per second, what's the unit for energy per second? Watts. Yeah, watts, right? So it's power, right? So this could also be written as the power delivered by the wave, right? I'll just say, I'm not going to write that part down. The power delivered by the wave. Think about like a laser pointer, right? You've got a laser pointer, you shine it on a screen, it creates a little dot at some distance, right? That dot has an area, right? And the laser beam has a power. In fact, usually if you have like a laser pointer, you can probably look on the laser pointer itself. It'll tell you the power of the laser. Similar to the problem we did a second ago here. Oh, this one didn't give us power, did it? Although we could have calculated it, I guess. So it's the power per unit area. That's what this thing represents. And this power per unit area is what we call S, which is going to be the Poynting vector, basically. Okay. So in a way, we could give this another name, because in, I don't know, what we're doing in my class in 1B right now, we're talking about sound waves, and how with a sound wave, if you're listening to the radio or something, you can crank up the volume, and by increasing the volume of a wave, in physics what we say happens is that you're increasing the intensity of the wave. So power per unit area is often referred to as just intensity. Watts per meter squared, right? Watts per meter squared. We're talking about, well, intensity, okay? So think about when you've gone outside and you stand in the sun on a really bright, hot day, and it's like really hot outside and the sun's beating down on you. You might say that, oh, the sun feels really intense today, right? Whereas on a day when it's a little bit cloudy, I haven't been outside today, but it looks like it's probably cloudy out there, the intensity of the sun's radiation is a little bit lower when it's not as cloudy, right? Because not as much light is reaching the surface, because some of it's being absorbed by the clouds, right? So the Poynting vector is designed to describe how intense is the wave. You know, how intense is the light that you're receiving, right? You can imagine something like a laser pointer. If you shoot the laser pointer, let's say at your skin, even at close range, it's not going to do any damage to you, right? But there are types of lasers that are used in, cutting gems and cutting metal and stuff like that. Those type of lasers, you wouldn't want to get them anywhere near your skin. And the reason is because they have a lot higher power per unit area. Anyway, so that's what the Poynting vector is this thing S, and we're going to say it's basically equal to epsilon naught times E squared times C in terms of its magnitude. But we are going to, so this isn't really the Poynting vector. It's really the energy flow per second per area, okay? But it is the magnitude, at least. We'll write it like that. This is the magnitude of the Poynting vector. There's nothing wrong with saying that. That is definitely true. It just isn't the vector itself yet. We're going to get there in a second. All right. So the way that we're going to do that is we're going to go back and use some of the definitions we had a second ago. We're going to replace C and E to get magnetic field back into this equation. And that might seem like a silly thing to do because we eliminated the magnetic field here, and now we want to get it back, but we won't have any plus signs. That's kind of the key here. So we want to use these equations again, basically. What's the best way to do this? We have an E squared times C. I don't know the easiest way to do this. Maybe replace C. B is E over C, right? That's not going to work. If we just replace E with C times B, let's see what happens. That should probably work. So we know that E is equal to C times B. If we replace that in this equation here, we're going to get that the magnitude of the Poynting vector is going to be equal to epsilon naught E times CB times C. And then we get that we can simplify this as E times B times epsilon naught times C squared. I'm pretty sure this is equal to 1 over mu naught because C squared from above was equal to 1 over mu naught epsilon naught. So if we plug that in here, we're going to get E B epsilon naught times 1 over mu naught epsilon naught. The epsilon naughts will cancel, and we'll get that the magnitude of the Poynting vector is E times B divided by mu naught. Now, in order to turn this into a vector form, what we're going to do is we're going to use the fact that we know that the energy associated with this light wave flows in this direction. It flows in the same direction as its as the velocity of the waves. The energy flow we know goes in that direction, but we also know that the direction S then is given by E cross B. So we can come up with our definition of what the Poynting vector looks like as being E cross B divided by mu naught. And that is the Poynting vector. So if you take the electric field of the wave, you cross product it with the magnetic field of the wave, which we know these are actually functions of position and time, right? Then you get the Poynting vector of the wave. This then, S, will also be a function of x and t, but what we're really going to care about is the average value of the Poynting vector. That's actually going to be what we care about. So what we're going to do is we're going to derive what the average value is. But before we do that, do you all have any questions? All right, from above, we know that our electric field was equal to something like, let's see, well, the first one we did was J hat E max cosine of kx minus omega t, and B was k hat B max cosine of kx minus omega t. So let's use this. We're going to plug these into this equation here, right? So S would be equal to E cross B, which is going to be J cross K, and then we have E max, B max, and because we're assuming that these waves are in phase with each other, there's no phase difference here. The omegas and the k's are the same. So this is just going to be cosine squared of kx minus omega t. And now, of course, what we want to do is we want to time average this over one period so we can figure out what the average Poynting vector is going to be. And it's going to be equal to I hat, j cross k is I hat, E max, B max. And can you all tell me, we've done this at least twice in this class, I think. If I want to average the cosine squared function over one period, what do I get? Or even if over an infinite number of periods, doesn't matter how many. What's the average value of the cosine squared function over one period? It's also the answer to the question, if I integrate cosine squared of kx minus omega t over 1 period dt from 0 to t, you put a 1 over t out in front, what's this equal to? We did this when we talked about alternating current, when we were looking up, we were trying to figure out RMS current and how it was defined. Maybe that's the only time we did it in this class. Anyway, what do you get? Anyone remember? The answer is very simple. It's not that tricky. Cosine squared looks like this. 0 is not the answer. Cosine squared is always positive, right? If you did the same integral, but cosine was to the first power, the answer would be 0. It's squared, exactly. But you're right. If this was just cosine, it wouldn't be. Yeah. Square root of 2. I think you get half. That's close, though. I think you get 1/2. You can try it yourself. And the main reason is because you can replace cosine squared here with something like, it's like 1/2 minus cosine 2x or something like that, right? This whole thing is replaced with something like 1/2. It's either plus or minus, it doesn't matter. Cosine of 2x. Whoops, not cosine squared. 2x over 2, I think. I don't know if this is plus or minus. I'm not sure what this number is. I can't remember. But the point is that this whole thing is equal to this, and then when you take the integral of the second term, you get 0 because it's from over 1 period, and the first term you get t over 2, and then you divide by t. That's it. Okay, so you get 1/2. So that means that the average value of the Poynting vector is gotten by just taking, well, now let's go back and kind of generalize it, right? Oh, and I left out a S equals this, which was E cross B, but I left out, there is a 1 over mu naught, which comes from the definition right here that I left out. So there's still a 1 over mu naught hanging out over here. So we say in general that our Poynting vector we can get by doing E cross B. Sorry. Let's just do magnitude, because that's what we care about in the end. Is going to be S average is going to end up being E max, B max over 2 mu naught. And this is mostly what I think you're going to use in your homework problems. You may have to use this one. I can't remember, but definitely you will have to use this version of it. Let me make sure that I actually wrote it down right. Yeah. And again, what this represents, they write it a bunch of different ways, but this is the right answer. So this is the intensity of an EM wave. And of course, because B max can be replaced, remember that you can always do this. So you really only need to know one or the other one, and then you can get that. But this gives you the intensity of a wave. And it gives it to you in power per unit area. Power per unit area. And we can use this to solve a problem here. Wait, power and pressure, that's... Sorry, we can't do this one yet. Not yet. So we're going to have our own problem here. This is where I'm going to make up a problem. So we can relate the Poynting vector to something that you can relate to, I think. So suppose you have a house. Okay, it's going to be a very simple house in order to make this calculation simpler. So let's say that you have a house, right? So here's your house. It looks really weird, but here's a door. Here's some windows. And on top of your house, let's say you have solar panels. So the entire roof of your house is covered in solar panels. Maybe you live out in the desert in Arizona. You live off the grid because you're an edgelord and you want to run your everything in your house off of just solar panels, okay? And let's say the sun is overhead. Okay, so the sun is sending down waves. And what we know is that near the surface of the Earth, the average value of the Poynting vector coming from the sun, I think it's 1400. I never remember if it's 1400 or 1000. I think it's 1400 watts per meter squared. I think your book talks about this. I remember this from a different textbook that I used in the past. But yeah, it doesn't, right? Anyway, so the average value of the Poynting vector is 1400 watts per meter squared, okay? That's near the Earth's surface. I think this is, I don't know if this is like when the sun is at maximum, like when at noon. It probably is. This is probably when the sun is shining directly down on the surface of the Earth. And then the value of the Poynting vector kind of goes down as the sun starts to set, and you're only getting some fraction of the Earth's energy, or the sun's energy. Okay, so let's say that your house has dimensions of 5 meters in this direction by 3 meters in this direction, okay? So that the area of your house is, what, 3 times 5, 15 meters squared, right? Let's figure out the amount of power, how much electrical power you can get from your solar panels. If the efficiency of the solar panels is 20%. Okay, so that's what we want to figure out. How much power can your solar panels provide at peak intensity if the efficiency is 20%? So we'll assume that this represents the intensity of the sun whenever it is directly overhead. And that's our area, okay? So to find the power, we're going to use power is equal to intensity multiplied by area, okay? Intensity is basically power per unit area. So in our case, since S average is also basically the intensity of the sun's light, this becomes S average right here times A. So if we plug in our numbers, oh, and we're going to have to also multiply by the efficiency factor, sorry. Solar panels, no solar panel is 100% efficient. The best solar panels are like 25 to 30% efficient, so 20% is pretty reasonable. We have to multiply by 0.20 for the efficiency here. So we're going to have S average times the area of your house, or the roof of your house, and then multiplied by 0.20. So we're going to get 1400 watts per meter squared times the area of your house, which is 15 meters squared. I don't know if that's a big area or not. 5 meters by 3 meters doesn't sound like a big house. Should probably use bigger numbers. That's okay. And then times 0.2 equals. So I get 4,200 watts, which would be the equivalent to 4.2 megawatts. So that would be the rate at which your solar panels would deliver energy to your home during the daytime. And of course, if nobody's there to use the energy during the daytime, all that energy would go to waste. But if you had some kind of like a battery system, like a power wall that Tesla sells, you could be charging up that battery to be used later in the nighttime or something like that. If the sun is at peak intensity for about 2 hours or so, then you could get about 4.2 megawatt hours of energy stored up in your battery that you could then use in your home later at night. But anyway, so it's just a simple calculation of the amount of energy that you can get from the sun, just based on this knowledge of what the Poynting vector is, right? And I didn't just make this number up. I'm pretty sure this number is correct, or roughly correct. It may be 1,300, something along this range right here. This value would be higher a little bit, I believe, if you're on top of a mountain, maybe not by a lot. A little bit lower if you're farther below sea level. But nonetheless, this is a reasonably large amount of power right here. So at 4.2 megawatts, what could you power with that? So when you buy a light bulbs are usually like 100 watts. And actually, the light bulbs that we use nowadays are even more efficient than that, right? The fluorescent light bulbs. I don't know what their rating is. I think that they're maybe 10 watts and they produce a ton of... Oh, it's kilowatts. I was going to say that megawatts is huge. Megawatts was a huge number. That something seemed wrong with me there too. Yeah. Okay. Yeah. Megawatts would be enough to provide all the energy you need for multiple days for a family, actually. Kilowatts, though, you'd have to be a little bit more conservative with your energy consumption if this is how much energy you received. Because, for example, running if you had like a washing machine or like a dryer, dryers consume a lot of energy. So if you have a dryer, for example, a dryer consumes about 5 kilowatts of energy. So this would not be enough to run a dryer. It would, however, be enough to watch television, to use your laptop, to charge your cell phone, to do all kinds of things that aren't like really major expenditures of energy. Major expenditures of energy would be things like running your air conditioning, running a 5x3 area. You mean 5 feet by 3 feet? Or do you mean 5 meters by 3 meters? Is 5 meters by 3 meters? Yeah, this would be like 15 feet by 9 feet. And 15 times 9 is about 150. So 150 square feet would be the area here. That's not big. That's not big at all, right? Because I don't know square feet really well. I don't go around like looking at apartments and stuff very frequently, but that's not very big. So the point is actually this would be a very, very small shack that you're living in that would be producing this. The reality is if your house was even, I don't know, 5 times as big as this or 3 times as big as this, you'd be producing a lot more power. And I'm kind of getting in the weeds here and I want to keep going, so I'm not going to go into more details, but there we go. Any questions? One other thing we could do with this is we could actually calculate the electric field component of the Earth at the surface of the electric field, right? Sorry, at the surface of the Earth. We could find what this is. If you know this number, and you know this, and obviously we know 2, and then you replace Bmax with this, so you get E over C in there, you can actually find the value of the electric field or the magnetic field of the electromagnetic waves coming to the Earth. So that's another thing that we could do with this. All right, we've been going for exactly an hour now, so we normally end at what, 3:15, right? No, 4:15, right? So we still have plenty of time. We still probably will finish a little bit early today because we only have one more topic to cover. But nonetheless, we need to take a break, so let's do that. We'll take a break for 10 minutes until 2:57. Wait, was I even recording this? Yeah, I was, okay.